Integrity is everything. Our way of life in this country rises and falls on the integrity of our leaders and the integrity of our infrastructure. Because integrity impacts everything, this is the Integrity Podcast, powered by EXO, hosted by Zachary Oliphant.
Well, welcome everybody. I'm excited to have our distinguished guest today, Mike Miller, with us. Give you a little bit of background on Mike, and Mike's got so many acronyms after his name, this might take a little bit, but Mike Miller is a professional engineer, and he is the Vice President of Technical Services at EXO. He's got 33 years of experience as a civil engineer in the electrical transmission structures industry, designing, analyzing, and testing critical infrastructure. Mike has a BS and a MS degree in civil engineering from Portland State University and is licensed as a professional civil engineer in over 20 U.S. states and several Canadian provinces. Mike is also a member of IEEE, CGRE, and is a fellow of ASCE and SEI, which is just a fantastic honor. And Mike, just want to welcome you here to the Integrity Podcast. Happy to have you and all of your knowledge and experience as part of EXO. But I'm happy to have you share some of that knowledge, impart your knowledge on the folks that are listening. Hopefully we'll have a great conversation today. So maybe just to start off, Mike, walk me through your background. Like how did you get into engineering? What drove you to engineering? And we'll start there.
Sure. Well, happy to be here, Zach. So for me, it probably started way back in grade school when one of my instructors, one of my teachers, set me aside and helped me with math. You know, math is very needed in the industry for engineering type of activities. And for me, I struggled at that time. This was in 7th, 8th grade. And he really helped me, kind of put me on the right path and showed me the ropes. And I remember Mr. Castleman, that was his name. And then after that, I learned long division, multiplication, and then I was into music. I actually took up an instrument, trumpet, started playing in the band. And, there's a relationship between musical notes and engineering. It's a mathematical relationships. And so that also, I think, had a big influence on me and what kind of drove me to engineering. And I kept with music for many, many years. And in fact, I still play.
Well, that's amazing. Something I didn't know about you, Mike. We'll have to have you play at the office one day. And so walk me through your education background at Portland State. Why did you gravitate to civil engineering, right? I mean, there's all these different engineering fields you could have gone down where math is certainly a huge component of them. What really drove you into civil engineering in particular?
Well, I was also interested in electrical engineering, construction engineering, which is a branch of civil engineering. But I gravitated towards civil structural. And I think what did it for me was I was doing problems, and I was taking a statics or dynamics class, I believe, and was doing homework problems. And for the homework problem assignment, instead of just writing it up on a piece of paper and turning it in nice and neat like you're supposed to do in engineering class, I created I wrote a program. I wrote a basic program that at that time, PCs had just kind of come out in the industry. And so I wrote the program to create the shear and moment diagrams and plot the shear and moment diagrams that were part of the problem. And so my instructor at the time caught on to that and said, hey, we got to get this guy. And so I started working for him in the structures lab of Portland State University.
Oh, fantastic. And so that was kind of the impetus of now you're a structures guy and have been there for decades now. Once you got out of school and you got your master's, then where did you go to work?
So as a student, I actually worked at Bonneville Power as a student doing work for them, doing drafting. And that was the time where you'd have a room full of drafting tables, and you'd see engineers, old school type engineers doing drawings. And so I started with them right out of school. I had several other offers, which I was I was happy for, but chose to stay in the Pacific Northwest, and this was after my master's degree, and started working on engineering and working on the electrical power structures that we see every day, lattice structures and tubular steel poles and so forth. And I really gravitated toward lattice because there was so much lattice, existing lattice in the system. And so much of my early career was just modeling those lattice structures. Several hundred structures were modeled, and I learned a lot by doing that. And of course, learned by just being around the other engineers and learning from them.
Absolutely. And a lot of what we discuss here on our podcast is that kind of joy of learning and continuing to learn and learn from others. It's amazing how that's kind of interwoven into almost every conversation, right? Who did I learn from? Who am I helping learn? Which I think is a fantastic perspective. So you're working for BPA, and you worked there for quite a while, working in the engineering department and leading the engineering department. And then you decide to go outside of the utility and go into the kind of commercial space. Kind of walk me through that.
Yeah, so at that time, Bonneville was in a big build-out where they were building out major 500 kV corridors, lines that were being done, and I was heavily involved in new design for them at that time. And then it kind of slowed down, and which is natural.
Mm-hmm.
These things come and go, ebb and flow with the different needs of the region and so forth. So, but I still wanted to do more design, and so I decided to go ahead and leave the federal government, the protective blanket of the federal government as well, and go out into the private industry. And so I moved. In fact, I did a geographic move. I moved to Houston, Texas, and worked for SAE Towers, which had manufacturing in Mexico and manufacturing in Brazil.
Absolutely. And primarily manufacturing lattice towers.
That's right. Primarily lattice, but also tubular steel poles.
Absolutely. So as you think, Mike, about your kind of professional career, maybe walk me through, and for the audience, kind of your current role with EXO and what you're doing today. And maybe we can then dive into a couple of examples, kind of seminal moments in your career that, as you look back, that maybe impacted you in some positive or negative way, but had an impact on you.
Yeah. So today, of course, I lead the data portal group, which is a group of individuals, data analysts and engineers that take that data in from our inspections and really put it up on the GIS server so that our customers can see and look at that. But at the same time, we're also evaluating that data and making determinations and ratings on the condition of that data, of all the assets. And so I manage that group and improve the data processes where I can. But that's one aspect. The other aspect is doing auditing of in-plant auditing. So I'm involved in the assessments and the processes for doing that evaluation of different audit for both lattice and tubular steel pole. And then also forensic type engineering. So if there's a failure in the field somewhere, oftentimes customers will contact us and we'll go take a look and do some forensic engineering to determine the root cause analysis of the issue of the failure, and then back out what happened and see that doesn't happen again.
Absolutely. So it's interesting as you think about our business, and in some ways what makes us unique is this kind of combination of this field data collection or inspection component, which is critically important we get right. And then you have the second piece, which is what do you do with all that data, right? And you and your team do a fantastic job in synthesizing that data and then being able to deliver to a client some actionable details on, where do we spend money to solve a problem, which is critically important. As you think about, Mike, in your history of being in engineering, are there some examples that come to mind where maybe we've solved, whether it's at EXO or maybe in your former career, where we've solved some kind of interesting and unique challenges for clients, and what that experience was like.
Yeah, just in the time that I've been here with EXO, we've had some excellent opportunities and some great challenges, and we've come up with some very unique solutions for some of these challenges. Some that come to mind are a tubular steel pole line that was an older line, weathering steel pole, which was at least 30 years old in the Midwest. And that particular line was corroding at the ground line, which we often see with some of these structures. And so we were tasked to come in and remediate. First, evaluate, determine the section loss of the poles, and then remediate that and do it in a cost-effective solution. Now, what was challenging about this project is this particular line was in a residential area, and these structures were in backyards of different homeowners. And so that created a unique challenge to do it in a way that wasn't too disruptive, that still met the need and reinforced the structure so that these structures could last, say, another 30 years. And it was successful. I mean, we were able to do that. We were able to do it, within the time period. We were within the budget that was allotted, and a very unique solution, which was a wrap of a certain structural components that reinforced the tubular steel pole at the ground line, which is the highest point of load on the ground.
And I imagine a real challenge for them would be tearing up people's backyards and rebuilding a line, which is always an alternative that utilities consider. But doing that in someone's backyard becomes really disruptive and pretty expensive as well, I can imagine.
Absolutely. And these components, we didn't have to bring in a crane to install them. These were all basically small enough that they could be lifted and by a person, installed one by one, and doing that in a systematic way, we were able to avoid some of these big disruptive construction activity type of things that of course, homeowners don't really care for.
Yeah, certainly in their backyard.
That's right.
Big cranes and whatnot. Well, maybe give me another example, Mike, where you think that you've kind of taken this synthesis of kind of engineering and inspection and data delivery with a client where we've solved another problem or where you solved another problem.
Sure. So, as you know, there's so much of our infrastructure in the U.S. is 40, 50, 60 years old. And that's not a bad thing. I mean, these structures, particularly the lattice lines that were installed in the 50s, 60s, and 70s, they still have a lot of service life. Okay, but they need to be maintained. And so one project, again in the Midwest, where we were asked to go and assess the condition of a particular lattice line, a double circuit line. So these are very tall structures and older, within, I think, a 60, 70 time frame. So we went ahead and did that and did a drone inspection, gathered data, and the decision that the utility was grappling with was trying to determine whether to replace the line or remediate the line. Okay, and so when we did that work, we evaluated the photos, took all the data, ground line assessments, and we determined that it was indeed remediatable, and it could be done in an efficient way and not too costly. So that, and that was very valuable, of course, for the utility to make that to have that data, and we presented it in a form, of course, that was easy to digest with our GIS-based, cloud-based system that we provide them. We go in and that rating system comes up, and they can select which structures needed attention in terms of maintenance or replacements of certain components, and which structures they didn't need to really worry about.
Yeah, no, absolutely. And I think it's interesting as we think about, I know Wes, who's on our team, sits on the committee to write kind of the condition of various components of U.S.'s infrastructure. And a lot of that infrastructure is D+, C-, and has some real age to it. Mm-hmm. I think the interesting thing we see in our industry is a lot of I'll call it the non-wood infrastructure is getting to an age now where it needs something done. And we're seeing, as you mentioned, utilities really grapple with this concept. It's old, I should replace it, is one kind of way of thinking. Or no, it's still perfectly good or mostly good, and I can make these little tweaks and improvements, and the line is actually will last much longer. Kind of walk me through your view if you're sitting in the shoes of a utility operator. What you believe you would need to be able to make an educated decision regarding those kind of two options, and maybe some of the struggles and some of the things you could find in a company like Exo to help give you the information to make an intelligent decision.
Sure. So as I mentioned before, the age of the infrastructure in general is 40, 50, 60 years old, and yet steel doesn't degrade over time. It can corrode if it's not maintained, and so I believe there's a certain push or tidal push to the industry, or replacement mentality, so that it's kind of like the throwaway mentality, but applied to structures, so that after a certain period of aging, because of that age, there's a belief, I would say, that a structure needs to be replaced, when in actuality, maybe it can be extended for another 60 years. I mean, there's no reason why these structures can't be extended indefinitely, given the right maintenance program, given the right proper attention to detail, like a company like Exo. So that type of thinking is everywhere. And of course, engineering, we learn from school, even university days, about build new. You learn how to build new. The emphasis is always to build new. Yet we don't really discuss in university the idea of extension, life extension, and what's involved in really assessing a structure for life extension. So our focus is, of course, life extension. And now, if a structure needs to be replaced, okay, if there's so many things that are degraded, it's been neglected over the years, and it's corroding everywhere, well, then at that point, perhaps there's a point of no return. But that point of no return, where you assess the cost of maintaining a structure or bringing it up to the current standard versus outright replacing the line, that difference is a lot different than it used to be. The cost of construction, of new construction in the U.S. has skyrocketed just over the last 10 years. Labor costs, construction costs, material costs, all these things,
environmental impact,
all these things have really increased. And so I think looking at that from that perspective, and looking at the condition of the line and assessing these key areas that only need attention, I think is really key. And of course, it's important that we highlight those areas and communicate those to the utility so that they can understand to make a decision on whether they need to make that full replacement, or whether they can extend these structures for another year and how they can actually do that.
Absolutely. And all of that cost ultimately rolls down to you and I and every other consumer of electric power, right? When that cost is passed into our rates, and we all have to pay for those things. And so certainly, at least having the tools and the skills to evaluate your options is really valuable. And we're starting to see, as a business and as an industry, more and more folks saying, wait a second, we don't always have to rebuild new. And I think you're right. Some of that's really being driven by some of these challenges. Right-of-ways are harder and harder to acquire. Environmental impacts, dealing with landowners. I mean, those are all really tough challenges in construction, which is, as you said, driving the cost up, and allows options like ours to extend the life of assets for decades, a really viable option. Walk me through, Mike, maybe an example in your history where someone taught you something that was just like an epiphany moment, right? Where maybe you were dug in a position and you said, okay, I think I'm right, and you're holding your ground, and then all of a sudden, oh, wait a second, that's an interesting perspective. Maybe I should integrate that. And that you mentioned continuing to learn. Kind of unpack that a little bit for me.
Sure. So our industry is a little unique in the world of structural design, structural structures, in that many of the structures that we design are full scale tested. Now, lattice is generally full scale tested because of all the complexities of all the connections. Tubular steel poles are based on structural components that have been full scale tested as well. That in itself allows us to really understand and comprehend the value of the structure, okay, and know its true capacity. If you compare that to a building where you're using load factors and other factors to assess and capture the uncertainty of the loading on a building with all the different things that are in a building and all the load paths, it's a very highly redundant system. Our structures are full-scale tested. They're verified. And so now, as part of that verification process, we learn new things. So, and I get surprised with every test. With every single test that I'm involved with, I'm learning a new thing. That might be the cross brace and the load flow through the cross brace. It may be a particular connection, a number of bolts, or an angle, which is made, we use mainly the angle shape to make all of the connections for a lattice tower, and that's an ideal shape for that because of the different flanges. But we assume in analysis that the load flows through those flanges in an equal way across the area of the full shape. In reality, the load goes through the angle in a slightly different way than what we assume. And so you might get more load in one flange than the other flange. And so these types of things are always new learning opportunities that we find when we test. So we always find something new that we learn when we test. And it's because we're taking it to the limit. In fact, we're testing it. Normally we test it to failure. So we really understand what the structure will be able to take in the environment that it's subjected to, whether that's wind, high wind, extreme wind, hurricane wind, ice with concurrent wind, heavy ice, or a security load like a broken conductor and its effect on the adjacent conductors, so we can avoid a catastrophic domino effect or longitudinal cascade of structural failure. So all these things we continue to learn, even though it's a very old industry in terms of age, 100 years, 70, 80, 90, 100 years old. And we've used structures. They're all over the U.S. They're all over the world. They're used worldwide. We continue to learn and enhance our knowledge because we're using them in different ways now. We're coming up with different configurations to meet our needs, and so it's always fascinating for me to continue the learning process and to really learn, but also apply what I've learned to new design or new evaluation of the structures. But I say that it's also important to look back at the history, because one of the first things that I do, and we do a lot of analysis of older structures, right, that have been in service for 50 years. We have to first understand and really get into the head of the original design engineer and the assumptions that were used in the original design, because that will help us really understand what's happening with the structure. And that can change from structure to structure. I mean, the public looks at a steel structure and they look all the same. They look like they're identical.
Manufacturers would be happy if they were all the same, right?
They would. But in fact, they're different. They have different characteristics, different wire sizes, which produce different loads. I mean, all these things that go into the design and analysis of these structures is very very unique across the U.S. And there must be over 400 or 500 different wire sizes alone that are used in the U.S., from copper all the way to the new hybrid type of conductors. So and that, of course, goes through the structure, and that's what we're supporting. I mean, the wire size drives everything.
Yep.
So it's important to really understand that, and testing helps us do that.
Well, and it's interesting, Mike. You mentioned the testing and structures being really designed to fail, right? Which is somewhat unique as an engineer in our industry. Kind of walk me through the desire to deal with the practicality of engineering and the conservativeness in engineering. That's kind of natural, right? I mean, you want it to just hold the load. And there's this pressure, somewhat pressure as an engineer, I can imagine, that you always want to pass the test, but just passing with flying colors is a problem too. So kind of walk me through that balance for you all as engineers where you're trying to get it right.
Yeah, there is a balance between the economies of a design, the efficiencies of the design, and the use and the cost, right? So you're always balancing that cost. And the first thing we do as engineers is we need to know what our lines are going to be subjected to for the next 100 years in terms of load. Mm-hmm. What kind of extreme winds, what kind of extreme loading are we talking about? And that's become already very complicated with climate change. Mm-hmm. All of a sudden, now we have a new variable to figure out and how we can implement climate change and capture the effects of climate change, because the climate is not only heating, but it's also cooling. So the volatility between the heating and cooling cycles are much more, say, volatile than in the past, and how that affects the transmission line, which is placed over the landscape like a big net to collect all the storms. We have to understand that, and we have to know the impact of any load differences so that we can incorporate them into design, and also do provide some kind of assurances to the public that we're actually looking at this, and we're actively looking at the impacts of climate change on our systems, the additional load, or in some cases the reduction in load due to climate change, and it's become a very big challenge.
Well, it's interesting, Mike. You mentioned the loads and the standards and the codes that drive our industry. Walk me through a little bit your experience. You've sat on lots of different committees. You've chaired various committees. I guess number one, kind of walk me through what you're doing today, and then maybe give me a little bit of historical perspective on your view of the value of sitting through that process, which is sometimes a slow and arduous process, but the value that you get out, or you think other engineers, especially young engineers coming up, could get out of being involved.
Sure. And it's always great to be a volunteer in some of these standards activities, and whether that's the American Society of Civil Engineers, or whether it's the IEEE or CGRE, or some of the others, ASME, things like that. So it's always very good for not only your knowledge, to improve your knowledge, but it's also good to be able to have a voice in that process and the decision-making process for new standard developments or manuals of practice developments. And so, yes, I'm in several right now. I'm chairing the loading standard, which is a brand new standard in the U.S. here under ASCE. It's called the loading standard. It doesn't have a number yet, but it involves elevating the manual of practice 74, which is the loading standard, how we use to get loads, up to an elevated standard that can be used by states as a model code to implement. And so I'm involved with that right now. We have our first face-to-face meeting next week. With COVID, it's been a little difficult, to get together. And then I'm also involved with ASCE 10 standard, which is the lattice design standard, which is an older standard, but it needs to be updated by definition every 5 years in order to be relevant. And then ASCE 48, which is the pole standard, same thing, poles in terms of strengths. And then I'm also on the substation 113 manual of practice. Now, the difference between a manual of practice and a standard is a manual of practice is optional, recommended. It's a manual of practice that it's optional, basically. A standard is a higher elevation, but it still, unless it's a mandatory standard, and these aren't mandatory standards, but it's really could be referenced then at the state level and brought under and made minimum loads as required. So it's similar in that way to ASCE 7, which is the building minimum loads for building standard, that other standard I'm working on.
Absolutely. And for young engineers, what would you say, what value could they get out of participating in some of these committees?
Yeah, so of course it's always difficult when you're a younger engineer to get involved in a standard because you're usually heavily involved in learning new things just to get your work done. But if you ever are in an opportunity to be able to volunteer on a standard, you get so much out of it, just being around the same like-minded people that have that experience that you can glean. Much of what I've learned is by going to these standards or manuals of practice meetings, because it's not only meeting and discussing, but it's listening. It's comprehending new things that may not even get into the standard. So a lot of the benefit of that is, a standard process is a consensus standard. So you're not going to get all the great ideas. It's going to be, whatever you can reach a consensus on. So there's going to be certain ideas that are presented or discussed that are lost. So if you're not there, if you're not in the room and you're not listening, you might not hear some of these great ideas, which could then develop over time and then actually get into the standard with enough consensus.
I think too, with some of the other folks in our business that sit on these committees and standards, is you lose a little bit of how the committee got to a consensus, right? What was kind of the horse trading, if you will, and understanding how it was built, and then coupling that with the intent of what you're trying to accomplish with whatever portion of the manual of practice or standard of code. And I think that gets lost on some people sometimes. If you're not in the room, as you're mentioning, some of the intent doesn't always necessarily make it into the verbiage that everyone is being held to, right?
That's right.
Walk me through, Mike, in your career. You mentioned testing and failures. I imagine in some of those tests, things didn't go the way you wanted and something failed prematurely. Kind of walk me through the experience of learning from a failure. Sometimes people say a mistake or what have you. Why is that valuable for engineers, and what do you learn when that happens?
So as I say, the industry is unique in that we actually do test full scale our structures and apply all the loads, and we see failures. So now what that means is, again, it's not a failure as we know the word is a failure, like you're a failure. It's not like that. It's a learning opportunity. And in fact, we expect, if we don't see a failure, then maybe we're being too conservative, right? So since we're designing to failure, and so if let's say, for example, we design a line for 120 mile an hour load, 120 mile an hour wind load, and on that particular span, well, if conceivably, if it reaches 121, we would expect the structure to fail. So that's the idea of designing to failure. Now, no one likes to see structures fail, and that's why, actually, historically, the industry has done very, very well. Utilities have failures, and there are failures every year from excessive wind, excessive ice, and so forth. But in general, I think we've had a very good record of failure, and it's because we are so diligent about design, about doing it the right way.
Yep.
So, and then, of course, as an engineer that's designing right on the line, If you don't see that failure, you'll notice that, and maybe you're as I said, you're being too conservative. But in general, overall, we see roughly for every test, about 15% of the time we actually see a failure. Now that's a lot of failures. But again, failure is not a bad word. Failure is a good word.
Yeah, certainly as a learning opportunity, and when it's done in that kind of controlled environment. And I think you're right, Mike. I think for the most part, all of the failure investigation work we do at EXO, most of the issues we're finding are not on the design side. It's usually on the manufacturing side,
That's
right? It's the application of those designs and the execution of those designs that have been tested and vetted usually and reviewed. It's usually the application or the execution of the manufacturing of those goods. And that part's its own challenge. And maybe as a quick question for you, Mike, as an engineer, where you're trying to design something up to failure or close to failure, and now you're taking your hands off and you say, okay, now someone else has to go build it and construct it and maintain it. Maybe walk me through how you think about that as an engineer, and those various other tradespeople that have to touch this material you've designed and hopefully design it close to a point where it will fail when it needs to.
Yeah, and that's a very good point. In the design world, in the engineering world, we make the perhaps incorrectly, but we assume that a piece of steel is a piece of steel, right? A weld is a weld. The dimensions of that steel are correct. There's certain inherent assumptions in that process. But we know firsthand on what we see that a weld is not a weld. A weld is a weld, and has to be done according to the codes and standards, AWSD 1.1 in our case, and it has to be done correctly. The same with fabrication of any component. If the holes are off, if there's some deviations and they're not taken into account in design, then it's not going to perform the way that it was designed and it was intended to, and that could be a problem. So the way that we can get around that, or the way that we can handle that, is by inspection. We need to verify. Trust but verify. We need to verify that the components that we've designed, or that any engineer has designed, is being fabricated correctly. And if you're not watching that process, if you're not verifying that process yourself or through another party, things can go awry. And we've seen that. And as you say, all of the majority of the issues that we see in the industry are because of this issue with fabrication.
Yeah, and I find it very interesting. Our industry, certainly around the utility space, the primary warranty that you see given by manufacturers is 1 or 2 year material and workmanship warranty, right? And it's a very small window for something that should last 40, 50, 60 years, or that you're designing to last 40 or 50 or 60 years. And I always find it somewhat amazing when you talk to utilities and you just say, hey guys, are you understanding conceptually you're carrying 48 or 58 or 68 years of the life of this structure under you as the asset owner's responsibility versus the manufacturer's responsibility. And I know in this trust but verify, Mike, that you're referencing, we've been very fortunate. We had a client here in the South that they called us out. They saw they had a problem, and they said, hey, we need to get some expertise in to look at this issue for us. And it just so happened that they engaged EXO about a month before their commercial warranty ran out. And in that particular case, the warranty dollars the manufacturer has spent has been in the tens of millions to try to resolve these manufacturing-related defects. And for this particular client, it was just luck. It was just luck that someone said, hey, we think we have a problem, which It's great that when an engineer sees something, they say, we think we have a problem. But then to say, I need to do something about it, engage somebody that has the expertise to solve it. And in that scenario, we end up saving the utility tens of millions of dollars that a month later would have been their warranty responsibility, right? The utility would have been maintaining that. And that part I find very interesting in our space. For so long, we've been trusting. And we used to do a lot of verifying, back in the 60s and 70s and 80s, when a lot of these structures were relatively new and people were still trying to get comfortable with them. Utilities used to send a lot of folks in the factory and oversee this, verification process you're talking about. And over the years, that stopped. And you've seen less and less and less of the utilities putting people in the factory. And you had this big gap, and now lo and behold, you're having all of these manufacturing problems, right? And we haven't seen, at least in our experience, utilities kind of going back to that, putting people in the plant. They're relying on subject matter experts like EXO to do some of that work.
And you wonder what's changed, and so what has changed though? What's changed between the 60s and 70s? Even if you have people in there, it used to be that you'd have a tubular steel pole and there'd be a defect and maybe the consequences weren't that great. They wouldn't cause a failure. It wouldn't cause a problem. But what's different now is our tools. We have computers. We have processes that allow us to design these structures down to the, minimized weight. And when we design to the absolute minimized weight, again, meeting the requirements, but in the past they were designed much more conservatively from a design perspective. So you had some more meat in the design that you could take advantage of. And so perhaps you wouldn't need a weld that was actually absolutely perfect. Whereas now you need that weld to be absolutely perfect because you've minimized the material, because you have the tools to be able to do that. And so that's been the change in the industry, is you have these tools and everything is being designed that way. It used to be that a structure for a span, you design the structure for the full span, and then perhaps it would only be used at 80% of that span. And so you have this 20% extra buffer. So you would. Well, now you can use the program to spot structures and be so optimal that you use 98% of the structure capacity with every structure. So you don't have that buffer anymore. And so as a result of that, everything becomes hypercritical. The welds, the position of the vangs, the position of everything becomes much more critical, versus in the past it could be, more loose.
Yeah, you're right. And so it's really kind of taken the onus that was primarily on engineers, and now with software where you can get everything really fine-tuned, it's shifted a lot more responsibility to the folks manufacturing. And the folks inspecting on the shop floor, right? And like you said, now you got to build it almost perfect. And if you don't build it perfect, you're going to have some real problems. And we see that all the time. As I think, Mike, kind of in your career, and you sit and think about integrity, and this is the Integrity Podcast, kind of walk me through how that word applies to your career, how you see that applied to the industry. And maybe an example of integrity and what you do every day.
Yeah, well, to me, integrity is everything, and it builds trust. I mean, if you don't have the trust, you don't have the integrity. But what I like to use or think about when in everything, my family situations, my work situations, it's I have a set of it's a 4-way test that I use. And this actually comes from Rotary, but before that it came from another issue that happened in Chicago way back many, many years ago. And that is, number 1, is it the truth? Number 2, is it fair to all concerned? Okay. Number 3, will it build better friendships and goodwill? Or goodwill and friendships, either way. And 4, is it beneficial to all concerned? And if you apply those 4 steps, those 4 tests to any situation, then you're going to have integrity, you're going to have trust, and you're going to build all these things that are desirable in our society. And so those are the things that I think those are the things that I use to help me make sure that I'm being who the person I really want to be in dealing with issues, any issue or life situation.
It's very insightful, Mike. And you think about trying to apply those 4 items, like you said, whether it's in your personal life or it's a engineering challenge, right? If you can apply those 4 items, you're taking the client's view into account, the fabricator's view into account, the line construction guy's view into account, and you're just trying to come up with the best solution. And I think that so much of what our business tries to do is surround ourselves with all these highly technical people. Sometimes we get in these fun discussions about, who's right or who's more right or who's better. But it's all built upon trying to get the best solution for the client.
That's right.
And I think as long as you're using that integrity and that best solution for the client as guiding principles and how you're getting there, I think ultimately what we've seen is you land at a really good spot for the client. And usually when you get to the best solution, it includes, the best way to deal with it in the field, the most economical way of resolving an issue. And like you said, you do that enough times, it builds trust. It builds trust with clients. And you have to have that in the type of work that we all do, whether it's engineering, inspection, what have you. As soon as you lose that, you're in trouble.
That's right.
Big trouble. The last question I had for you, Mike, is as you look back on your career and you're thinking about a young student just coming out of school, engineering school, and you were to look to them or chat with them, and you do some of this in your everyday career, what is the advice you would give them on how to be as an engineer, how to be as a person, and how that can be valuable to them and to their career and then to whoever their employer is?
All right. So my advice is to younger students that I meet or talk to is to have an attitude of being a lifelong learner. I mean, when you get out of school, that doesn't end your learning. You need to keep learning. And in fact, you do normally in engineering. Engineering is all about continuing to learn and applying those things that you've learned to new projects and new relationships. Relationships evolve and learn the same way. So you would apply the same thing to your work environment as you would in your personal environment. Things evolve and change and usually always get better. And you might have some points of going down or hiccups along the way, but in general, continue to have the positive attitude, continue to know that things are going to get better, and they always do, and having that attitude with everything in your life is, I think, important.
So, Mike, one of the things that's interesting to me is thinking about how all the structures that you deal with every day and our team deals with every day, how do they impact the grid, not only today, but as you look forward in the future?
Yeah, so what's interesting about the grid is it's considered one of the most complex machines that human beings have ever produced. I mean, very complex. The thing about electricity is you need to use it the moment that you make it. It has to be used and created and used. And that process, of course, has to be balanced. So with our structures, of course, we're supporting all these lines, and we're making sure that they're resisting all of the loads, and I lost my train of thought, resisting all of the loads. And the thing about lines is you have, normally a grid is developed based on assuming what's called a n-1 contingency event. What that means is any one line can go out of service and the rest of the grid will backfeed itself and keep the grid up and stabilized. Because if you start losing 2 or more lines to any portion of the grid, you can start affecting the voltage and that voltage drops, and then you start having to shed load. There's a whole remediation scheme involved in the operation of the grid. And so our structures are critically important, of course, that they're strong enough and they withstand the storm events that we expect them to withstand, such that these N-2 events, if they occur, or what's called black sky events, very, very large storms, will not impact the grid. And an example of that is Superstorm Sandy. Okay, remember when that occurred on the eastern seaboard? It took a lot of structures. They lost over 80,000 wood poles in the distribution side. But the transmission side, that's the backbone, it remained pretty well. I mean, it didn't really get affected that much. And so, again, very good performance on the grid. And so we have to keep in mind and keep that to the center of our mind, that we understand our process that we use for design is critically important to keep the grid up and running, because outages are not acceptable today. Yep. They're much less acceptable today than they were even 20 years ago. So it's important, and we have a lot of pressure to keep that going. And so we need to do due diligence on the engineering side to make sure that we meet the requirements of the load, make sure that we are doing what we need to do to keep this system in check, and doing it with integrity, of course.
Absolutely. And it is always interesting, Mike, where a lot of folks that aren't in our industry, you just turn the light switch on, you expect it to work. And it is a very complicated system to go from generation to light switch working, and all of the hardworking men and women that make that happen behind the scenes. It's a terribly complex industry. And, I'm always excited about our impact on that industry and how we can help support our clients, which is just fantastic. Well, Mike, I really appreciate your time here today and your insights and your knowledge and your experience. I want to thank you for all that you bring to EXO, which is really, really valuable. And hopefully the folks that are listening today, especially young engineers or utility operators, learn something today, and really appreciate your guidance and expertise at EXO. So thank you, Mike. Really appreciate the time.
You're welcome. Thank you.